Right, so good afternoon, everybody. So I do see people there at the back. Come up front, come up front. We are really want to sort of engage a little bit more with you. And just to remind, my name is Johan Enslin. I'll be the moderator today. And we have a great dream team here for you, and we'll introduce them soon. But let's first get started and make sure you understand how the questions and answers work. So basically, as soon as you have a question, submit it through the portal. So use the app, scan for it, and submit your question. The sooner we get your question, the easier we can actually manage the question. So I really appreciate that, and thanks for joining our session. So our session today, there's the code. As you can see there on the right-hand side is the code. So please scan it and get going. So a little bit about our session today. So our session is really about how do we see this energy transition is going to impact the new generation. All these great ideas you guys saw in the summit, how's this going to change? How do we interconnect things, right? A little antidote is that, you know, we do have a grid of about 1.3 terawatt right now of interconnections. That 1.3 terawatt is great, but unfortunately there's also 1.3 terawatt waiting to interconnect to this grid of new generation. New generation, large load. We'll talk about that a lot today. And I do want to start off with introducing our team. So we have here Jack, and Jack is going to talk about, you know, maybe things which we need to keep in toss. We'll see. We'll see. And then we have Peter. So Peter is great. He's going to, he sort of was a great mentor, both for me and for a lot of people at ARPA-E. And Peter is going to talk about things, how do we actually move energy much quicker throughout our country. And then Olga is really our semiconductor device person. And she's going to talk a little bit about today about AI and what is happening on AI in terms of our load. And lastly, but not least, is Mario. And Mario is going to talk about how do we connect these things in nice synergy? How can we get synergy about all our connections? And somewhere in between, I'm going to talk about the grid of the future. At least what I believe, and I hope that's where you're going to help us making that a reality. So thanks a lot. I'm going to introduce Jack first. Thanks.
Okay. Well, thanks, Johan. So I'd like to take a little bit of a different, approach here. We're about to toss out 300 years of dependence on fossil fuels. It's a pretty big transition. And I'd like to pose the question, what are we going to keep? What are we going to toss? It's kind of a fundamental question whenever you're trying to make a change. And to give you an idea of the challenge, but to simplify it, we're going to talk about a simpler transition. In Boston, they have a tradition called Moving Day, where on one day, 250,000 students have to move into an apartment and out of an apartment. And they have to do it quick, and if you're a student, you want to do it cheap. And it's sort of an interesting thing to contemplate because there's a whole diverse set of solutions that are proposed when you have 250,000 people. And it's interesting because you look and you see a pile of stuff, and you can't tell, is that a pile of stuff that you're tossing? Or is that a pile of stuff that you're keeping? And, it has implications because you can go fast by throwing everything away, but then your parents it's not so cheap because they have to pay for a lot of stuff that you replaced. And so these are the kind of dilemmas you have in a transition. Now, the consultants will always tell you that when you're making big choices, you can't always get everything you want. And in our case with our energy transition, we want it to be cheap, fast, and green. And a lot of times when you're making big changes, you can get one or maybe two, but it's really hard to get all three. However, we're ARPA-E, and we want all three. That's just how it is, right? We're pretty demanding. And, that means we have to think carefully about what we're going to keep and what we're going to toss. So I want to take you down the path that I went, but I'd be very interested in hearing what you think we should keep and what we should toss. And what I'd like to suggest is the way I came to my conclusions was by taking three steps in the approach. One is to look at a system-level investigation of our energy systems. And then what I was led to is, boy, maybe we don't want a lot of tossing going on. Maybe it'd be good for us to keep our grids and our hardware, and I'll explain why. But if we're going to do that, what we really need to focus then on is environmentally friendly drop-in fuels, which has not necessarily been the focus of a lot of our research here. So let's go down the path and see if you think that we can get all three, and if you have a better idea, we are all ears. So we already know what we're going to toss, right? We're going to toss 80% of today's energy supply. So I challenge you to go into your homes tonight or whenever you get back and toss 80% of the stuff out. Chances are that's going to be pretty disruptive, but that's exactly what we're going to do. 80% of our energy supply today is fossil fuels, and that's what we want to get rid of. And we are going to replace it someday with something else. And that something else is our choice. It could be electrons. We talk about hydrogen. We talk about ammonia. But we've got to replace it with something. And that leads to a lot of decisions. So, we already decided we're going to toss our historical energy production, this fossil fuel that we depend on. So that's 80% of it's gone. But the energy system is more than just the fuel. The energy system's an entire ecosystem that's evolved over hundreds of years. And it includes our energy storage and delivery grids. And it also includes the end-use hardware. This is the cars, the water heaters, the power plants, everything. All this stuff is like trillions of dollars of stuff. And so one of the things I think we want to ask is, we're going to toss the fuel. Do we want to toss everything that's associated with those fuels? Because remember, we're trying to do it cheap, fast, and green. And I submit to you that that may not be a good idea to toss everything. So why? Why is that? And let's start focusing, because I'm an engineer, let's focus on cheap, because engineers are all cheap, right? We don't really like to spend money that we don't have to spend. And so let's look at where the money is in the energy system. Now, we always focus on the cost of fuel. You know, you go to the gas pump and you pay $3, and the next day you pay $3.50, you feel that pain immediately, right? But that's not where the money is. The money is really in the storage and delivery and the end use. It costs about 10 cents to $1.50 to pump oil out of the ground. You pay $3 to $5 to put it in your tank. In a year, you'll pay maybe $1,000 for gas. That car, that end-use device, new one costs $50,000. That's where the money is. So that's kind of the distribution of money. Let's talk about our energy systems. We have multiple energy delivery systems, and the smallest one is the electric grid. It's also the most expensive. If we're going to toss out the energy delivery systems that are associated with the fossil fuels, we're throwing away trillions of dollars of assets, and we have to replace that with something that's going to be very expensive. There's one more energy system. We're already tossing out oil and gas, but I don't want to forget about coal. We move millions of tons of coal. And when we toss out the coal, are we going to toss out the delivery system for coal? And I suspect a lot of you may haven't thought about it, but Peter has some good ideas for what to do with that stuff. So we talked about the delivery systems, but what about the trillions of dollars of end-use hardware? 250 million cars, all of our facilities that use fossil energy to produce electricity, boilers, everything down to the home water heaters. If we're going to replace all that stuff, it's going to cost a lot of money and it's going to take a lot of time. So what I'd like to suggest is let's maybe think about what we want to keep and what we want to toss. And it may not be good to toss out all this hardware. Instead, why don't we focus on trying to find some drop-in fuels that allow us to repurpose this stuff? And there's all kinds of possibilities. And again, I'm very interested in your input, but I'll pick out two molecules that I think are interesting and maybe you haven't thought about. One is dimethyl ether, which is, comes from condensing two methanol molecules, and the other is renewable propane. Both of these can be made relatively easily and fairly inexpensively. And what's interesting is each one of these could drop in to replace something on the order of about 50 ecajoules out of the 100 ecajoules that we use today with no inventions. These things are commercially used in some cases today. The second question is where to make it. And if you saw Evelyn's really neat presentation yesterday with the overlays, what we need to do is overlay where the renewable energy resources are with the energy delivery grids and the demand. And when you overlay those systems, the nodes, the points of intersection, that's where you want to make this stuff. So what I'd like to suggest to you is that we think hard about what we keep and what we toss. And I'd like to submit that I think we can build the future clean energy system in the United States, starting with the foundation that we have today. And if we want to do it cheap, fast, and green, that will be our best path. But open to hearing your thoughts. Find us at Coffee with ARPA-E, either me or my colleague Jim Seba, who's also a keeper. So with that, I'm going to turn it over to Peter. He's going to tell you what he's going to do with all those coal shipments.
Thank you. Thank you, Jack. I made a list of important things to work on in the report here at ARPA-E. And one thing came out clearly on top, and it's how we store and move electrical energy. And I explored an innovative pathway, which I call electrons as a shippable commodity. When we look at solar and wind, and this is a study from NREL, it was also in the presentations from Evelyn yesterday, we have an incredible historic point where we can produce one of the lowest points of cost of power in history. The Midwest and the South are excellent places to produce a low-cost power. And if you are in North Texas, Oklahoma, or Kansas, you are in the pinnacle of an opportunity where you can produce power at historically low prices. But when I look at my energy bill, I pay a lot more. I pay 10 to 15 cents, and if you are perhaps in California or the Northwest in Boston, you might pay 30 or 40 cents a kilowatt hour for your electricity. And when you look at that bill, you'll find that 50 to 75% is transmission, distribution, and taxes. I want to find new ways on how to move low-cost energy from the places where it can produce at very low cost to the places where we have high loads. And I'll give you an example. Ashburn, Virginia, one of the places with the largest concentration of data centers, asked me, how do I get 3.5 gigawatts of extra power for my future data center demand in about 3 to 5 years? If they want to put that amount of solar power in that particular county, they would have to cover half the county with solar. That's not an option. Another path would be to put 5 times the transmission lines down. Not very popular either. Plus, it takes a lot of time and a lot of right-of-ways. So how do we get that power there is something that I want to talk about. Jack already showed you that we use rail, road, and waterway to move coal and other energy sources at scale and using existing infrastructure. And I want to explore how can we move electrons in the same way. And the principle is very simple. I want to graduate electrons from their wires and bring them to the big league of energy, and that is moving them in bulk. Can we charge something at the renewable sites, move it across the country to where we might want to need it, hook it up behind the meter or at the distribution center, return the empty system back, and recharge it. Now, the important parameters there are that we need to do this safe, but the second most important parameter is that we need to have something with very large energy capacity. And if you look at current energy storage systems, they look something like this. About 5 megawatt hours of capacity, that's 5 megawatts for 1 hour. And typically they charge and discharge in a time frame of 1 to 2 hours. They are used as backup in case the power goes out for a data center or any other application. In the scheme of things, 1 or 2 hours is relatively fast. So I talked to my kids, what's very fast and very agile? And we came up with the cheetah. So I call these cheetah batteries. We already have a program on their way to actually make more energy-dense electrochemical systems, and that's Propel 1K. Propel 1K is a fantastic program. It focuses on higher energy-dense systems that allow us to move trains, ships, and even airplanes fully electric to the skies in 10 or 15 years from now. The energy density for Propel 1K is 1,000 watt-hours a kilogram. And that allows you to take the same shipping container kind of type format and put 27 megawatt hours in. That is already an incredible leap forward. Now, I did ask my kids again and say, what is a little bit slower than a cheetah and a little bit bigger? And we came up with a cow. I asked Hallie if that was okay. He said, fine. But I want to take it further. We really need to get serious in how we move electric energy. And taking a 1,000-volt beautiful DC from a solar farm and then turning it into 60 hertz to move it through cables that you have to build and all these structures you got to move, it's a lot of work. Other ways how we can move this using very big energy storage systems. And we came up with a concept where you would charge something over a much longer time. If you are hooking up to a solar farm or a wind farm, you don't have to rush. In Propel 1K, you probably want to use that energy in tens of hours. Here I'm talking hundreds of hours or even a week. Can we get to 50 megawatt hours per single shipping container? And can we take such a system, can we achieve that by lowering the charge rate? If you look at the Ragone chart, there's the power on one side and the energy on the other side. If you slow down the charge rate, batteries really like that. A lot of parasitic effects are reduced if you slow down the charge rate, and allows you potentially to put more energy into such a system. And just to keep up the animal analogy, I call these whale batteries. How do I get myself some of those whale batteries? Now, I read a lot of papers, some really great research from Jeff Dahn at Dalhousie University, explored beyond lithium chemistries. How can we use graphene and bipolar structures to really increase the packaging density of electrochemistry into such a system? Some really exciting work. Another area I'd like to look at is multimodal batteries, where we have a particular state where we charge and discharge, but also a state where these systems are kind of passive and they can be moved easily. You can think of temperature or pressure or other mechanisms to activate these different states. And the last one we need to do, reduce loss mechanisms and extend the life. Now, if you did the math quickly, a 100-hour battery and charge and discharge gives you about 30 cycles per year. And since a typical battery can do about 1,000 cycles, I'm already looking at a system that can do 30 years. But can we really do something effective with a state of charge to extend the life of such a system so that its amortization and financial asset can be managed for a much longer time? Now, I'm going to give you an example of what that would mean if we would take such a system, 50 megawatt hours, and move it by train. You might think trains run on diesel. Is that a good idea? I'll tell you a secret. Trains are really already hybrid. Most of the diesel trains you see are diesel gensets sitting on an electric frame. If I tow 240 cars of energy behind me at each 50 megawatts, I'm pulling 12 gigawatt hours. 12 gigawatt hours is 120 megawatts for 100 hours. That is a movable power plant. The second question might come up, would that clog up our rail system? When I started looking at rail is quite incredible how much you can move with that. Currently in the US, we move 1.6 billion tons by rail, and a single train like that would represent 0.00045%, so it's negligible. Does it make sense from an economics and from an efficiency point of view? If you look at the energy you need to move it, and if you look at our ability to ship over distances, you can calculate using some of the assumptions I have here that you can approach something in the order of 5 cents a kilowatt hour delivery over 1,000 miles. And that includes the return trip. The second number here, 90% efficiency. So you need some energy to move. With an electrified platform as a rail system is actually quite effective. The best part here, no new infrastructure. This can be developed modular, distributable, and could start in a very organic growth fashion. Beyond rail, we also have shipping. The Missouri and the Mississippi are fantastic potential future electron pathways. If you really think about this option of electrons as a shippable commodity, we already talked about energy transfer, but also it's dispatchable backup power. If you see a winter storm coming, and typically the weather forecast can tell you 3 or 4 days ahead that something bad is coming your way, one phone call to Chicago can send you a modular mobile power plant by train to back up your grid in case something happens. That's pretty exciting to me. Arbitrage, I did the math myself. If you go from 5 cents a kilowatt hour at 12 gigawatt hours, the train, you charge it in the Midwest, you sell it in California at 30 cents. There's a significant amount of arbitrage you can manage with such a system. But I'm mostly excited about a completely new modality of moving energy. It's time for electrons to get serious and to join the bulk shipment league. So to be short, we heard already that a lot of renewable projects are waiting transmission and hookups. Moving electrons through new mechanisms is what we really need to explore, and I want to hear more about that from all of you. Moving electrons in new ways will unleash our full renewable potential that's currently stuck on our transmission projects. I want electrons to move the big league of transport. You have to press hard on these. And really come out of the wires and become a mechanism very similar to how we move tons of coal, gas, and other mechanisms today. It will also allow us to store the real energy density of electrochemical systems is going to be very important for us in the future. And I need your ideas in this, and to me it's not sure yet whether that particular pivotal point will be 5 megawatt hours, will it be 27 megawatt hours, or will it be the 50 megawatt hour wheel batteries? But I do know for sure that at some point, this is going to pivot where we're going to get electrons as a shippable commodity. And if you need to remember one thing, just give me some of those wheel batteries. My colleague Johan Enslin will now talk about taking DC voltage systems to the next level. Thank you.
Thank you. Thank you, Peter. So I guess Peter said we don't need the grid, right? Okay. Well, wait on this. This is not really true. But let's see. Okay, so first of all, we know how to transport people, goods, and stuff by rail, and of course, highway systems. Our automotive highway systems are the best in the world. So if you take that into account, if you look at the electrical grid on the other side, our electrical grid looks really like our city roads. Our city roads are the roads which basically connect regions together and counties together, and it doesn't really go into this highway system. So it's high time that we look at our grid today and realize this is really a regional grid. It's an AC regional grid, and what we need to connect all these renewables in the middle of the country, right here in Texas, to connect all those renewables, there's enough energy here to supply the whole country. No problem about it, just in Texas and Arizona. So we've got offshore wind. All of these are places where there are no people, or very few people. So let's go one step further and say, if we can overlay on our existing grid an HVDC grid, a DC grid which can actually control power and not just wait for power to flow its own way, but control power to go from the middle of the country to the East Coast to the West Coast when it makes sense, right? So think about that. Why would we need this? First of all, we've got a very old infrastructure. This infrastructure, we're not going to toss it to Jack's point. We don't want to toss it, but we actually want to release capacity in it and build something on top of it. Using existing infrastructure and using basically the same right-of-ways. That's sort of a key. Using the same infrastructure, the same right-of-way, but build 3 times more capacity. Why do we need 3 times more capacity? Really, if you look at the loads which are coming our way, we've talked about the renewable generation, but the loads coming our way, data centers, electrification of transportation, there's EIA reports which you can go into, which I think is actually very conservative. But those reports tell us that if we don't really understand what's happening, we really miss the boat on the future transition. So we have basically 3 times more electric load, which is going to come to our grid. Traditionally, the utilities planned for a zero growth or very little load growth. That is going to be thrown out totally out of the water because of those 2 main components. We see it also coming to our system, more energy storage. Peter showed us how we can actually going to have energy storage all across our system. That has to be interconnected somewhere to go to a load. So hybrid electric and hydrogen systems, which really are basically our storage backup systems, needs to be interconnected. And I believe hydro. Hydro meaning large-scale pump hydro, but also smaller-scale hydro in mines, in wherever there's gravity, we're going to use pump hydro. And there's a lot of unpotential in that storm of storage. So how's our grid evolving? What about microgrids? What about virtual power plants? Where are those playing in? Well, it's all interconnected. It's the grid of grids where the microgrid's going to evolve into virtual power plants. These virtual power plants need to be interconnected when it makes sense, economically, technically, resiliency-wise. So those need to be interconnected. So this is not an or situation, it's an and situation. It's microgrids and a macrogrid. So from that point of view, I think it is time for us to design that grid now, because this grid is actually going to move our energy from the East Coast to the West Coast. It's going to move energy from the middle of the country outwards when it makes sense. We have time zones to play with. We have winds cycles to play with. And that's natural energy storage, which really is sitting in our atmosphere. So taking that into account, we are at the point now where we can balance energy much better if we can move it instantaneously from one point to the other point, right? So let's talk a little bit more about this DC multi-grid. So, this is a line of showing distance versus investment cost of how much it costs to build a transmission line. Right, if we think about the AC terminal cost, our substations basically, that's sort of a fixed cost, and depending how long we built the line, that gives us an idea of the total cost of that line. Right, so what about DC? We know DC is an expensive technology, right? So why? Because the terminal cost, the DC substation cost, is actually very expensive right now, because there are not a lot of them actually around us, right, first of all. Now, secondly, if you look at that flat line, what do you see? There's a much lower slope. So we do know if we can build the substation in, actually the length doesn't matter. We can build these lines very, very long. Doesn't matter, as long as we build those substation costs in. So that's obviously the opportunity. How can we actually get that substation cost to the point where the DC terminal cost, the AC terminal cost is very comparable? They use same size, and they actually use the same sort of right-of-way in the example I show you. In that case, we can actually make this grid also much more reliable, because DC is controllable. AC is not. It depends on load flow, where the sort of natural flow for power is. In a DC grid, I can move that power instantaneously where I want to have it if I have this multi-terminal grid availability. Right, so we can control now power. We have a resilient grid. And by the way, we can get 3 times more power from it. So why don't we do it? Why? Well, before, we have to actually get right-of-ways. We have to get permits. We have to get, it takes a lot of time to build HVDC grids. So what we propose here is really think outside the box, where we can use existing infrastructure in roads, in rail, in existing AC lines to actually build this grid of the future. The existing grid of the future in a DC environment, we can take the same right-of-way, the same sort of area, we can move 3 times more power. We can actually even take the same tower, we can take the insulators off, we can move the wires around, and we can pretty much power our system with up to 3 times more power in such a scenario. Right, so here's an example or two of today's technology of where we are with HVDC stations. This is an offshore station in Europe, and this station actually is built, it's existing, it's existing station, but look at the size of that station. If you look at the cross-sectional diagram there, you see there is actually a lot of stuff in that substation. It's a converter piece, it's the switchgear, it's the transformers, and it's all isolated, it's different pieces. And by the way, if you look at the right-hand picture, what do you see? A lot of air. A valve hall is a fantastic place to be in. It's one of those really nice places to look at. But it's mostly air. There is a lot of semiconductor and a lot of controls in it, but it's mostly air. So what are we trying to do? We're trying to do in a potential new program, shrink the power electronics. We think we can actually shrink down the station design with gas installation, maybe solid-state installation. And I think we can also have to show how we can operate an AC and DC hybrid grid in the future. Right, so moving this from a traditional grid to a new grid where we actually can build these stations much more compact, much shorter, in a much more compact and a less expensive time. So you can see the modern HVDC station will fit in the same footprint of an future of the existing AC grid. And of course, the cables are there as well. So for a call for action, for all of you in the audience, we do need to do this sooner than later. We have to design that grid today. It has to have 3 times the grid capacity, and by the way, using the same grid infrastructure. So please come and talk to me about these opportunities and tomorrow and today. Thank you very much. And I think Olga is going to talk. Sorry. Thank you. So Olga is going to talk next as why do we need this grid of the future? But anyway.
Thank you. I'm Olga Spahn, ARPA-E Program Director, and I'd like to talk to you about how are we going to address AI-driven computing energy needs. Emergence of AI has potential to transform our lives, and that is driving the computing demand and data center growth to unprecedented levels. Part of that has to do with the fact that the model sizes are enormous and growing quickly, 6 orders of magnitude in 6 years, and there's trillions of parameters involved, and all this requires massive parallelization of resources. Not only that, but the energy demand associated with all this computing is increasing exponentially, whereas the growth of all available energy in the world is increasing linearly. If we do nothing, sometime in a near-distant future, sometime in the 2040s, we are heading for a moment where computing is poised to consume all available energy. Clearly, that is not tenable, and the builders of data centers and operators of those data centers are aware of that, and they are scrambling to secure additional energy to power their data centers sustainably, as well as carbon credits. So you hear about Google partnering with Fervo Energy, who is an ARPA-E awardee, by the way, on enhanced geothermal to supply their new data centers. Microsoft is courting small modular reactors for their new data centers. All that amounts to is increasing the supply part of this equation. That's increasing the slope of the yellow line. We also have to pay attention to the consumption line, the gray line. That is improving the energy efficiency of computing. And if we do that, we will unlock really the potential of AI. Otherwise, we will end up being limited by energy. So if we examine where is the energy actually going in computing, interesting thing emerges. I'm showing here on the left how much energy is consumed in flipping a bit in a transistor. Blue shows the situation in 2008, red is the 2018, and the trend continues today. You see, there's been a lot of progress made in reducing energy consumption of transistors. That's Moore's law in action. Transistors are getting smaller, energy required to change state is dropping. The minute that bit is flipped and you're trying to move it to the next gate or the next register, you find that you are expending more energy on that data movement. This is still on chip, just getting it a few millimeters to the edge. You spend more energy moving that bit than you spent creating it. And when you try to get it off chip, that's when you really pay the energy cost, and it just goes worse and worse the further you go. And it's not just energy. It turns out that you also don't have the bandwidth to get that data off the chip. So data piles up on the chip waiting to get off, and that causes further system inefficiencies downstream. People became aware of that and started examining ways to address this problem, including programs like Enlighten that ARPA-E has and other agencies in the same area. And they decided that maybe we should look at moving data not electrically, but optically. It turns out when you move data optically, your losses are a little different. They don't increase with distance. And we know this because when we move data for telecom or datacom, that's done over fibers, not over wires anymore. But where you do pay in energy when you move data optically is at the interfaces, at electro-optical and back conversion. So as that efficiency improves, it turns out that crossover point at which becomes energetically more favorable to move data optically versus electrically gets shorter and shorter. And so you not only win in energy, you also win in data capacity or bandwidth. That's because you can put many channels of information on a single fiber due to techniques like dense wavelength division multiplexing, for example, because photons don't interfere. And you cannot do that in the electrical domain. You need more physical wires. So people are looking at tackling this problem to technologies like co-packaged photonics. And that's really bringing a lot of energy efficiency, but it also opens up opportunities in data architecture, in data center architecture and topology. This is sort of notional sketch of what the architecture looks like today. You have these gray boxes that I'm going to call servers. Servers contain racks. Racks contain compute and memory resources like GPU, CPU, RAM, and so on. And those are interconnected by layers of switches. You already have optical interconnects at the higher levels. Data moves optically. Switching itself is still done electrically. And the lower levels, and certainly interconnections into the servers and racks, are still electrical. As the optical interconnect penetrates into shorter and shorter distances, that opens up new opportunities in data architecture. Like now, you can eliminate a whole layer of switches. Your switching itself is done optically. You can allocate your resources in servers and racks differently. You can disaggregate them. All the memory goes together. All the compute resources go together. And you can interconnect them dynamically using optical switching at these switching layers. And now you can match the resource connections to the algorithm you're trying to interconnect, and you minimize some of these bottlenecks with data movement, and you end up with a much better hardware utilization efficiency. And this brings you closer to what you're ultimately trying to achieve: improving performance for minimum energy consumed, improving energy efficiency of computing, improving energy efficiency of the data movement, decreases that denominator. And you want that. But you also want to improve the performance, and that's the numerator. That amounts to solving what I'm calling the traveling salesman problem for data. You want to optimize its movement. You want to remove those bottlenecks and imbalances in compute and data transfer rates. And you can do that through optimizing data movement via algorithms, hardware, and topology. And to get to that, you need advances in a number of different fields. You need to continue improvements in the efficiency of data movement. That is silicon photonics, improvement of electro-optic conversion efficiency, monolithic integration, pushing the optics deeper into the chip even. You can't neglect ongoing improvements in compute efficiency, right? So that's where you have both CMOS technologies you can bring to bear, neuromorphic computing, quantum, spin, and all that stuff. And most importantly, there's opportunities in data movement management through co-design of algorithms, software, architectures, and hardware like optical MEMS and 3D heterogeneous integration and high bandwidth memory. All of that to eliminate, minimize, and coordinate data movement. If you have ideas in this space, I would love to hear from you tomorrow at Coffee with ARPA-E or via email. So please find me and let's talk. Thank you. And now, last but not the least, Mario.
Thank you, Olga.
Yeah.
So hello, everyone. I am Mario Garcia-Sanz, Program Director at ARPA-E, and I would like to talk about something that I believe can be the next revolution in renewable energy. And this is around the concept of synergy. However, you will see very quickly that synergy can be very dysfunctional. I mean, it depends on the co-design of systems. So the idea is to co-design renewable energy systems physically in a way that we end up having solutions for very critical problems that we have today in the grid and in other aspects of energy. So let's start with a couple of problems that we have today with the grid. The first one is intermittency. Renewables actually are not very good in terms of what we call the capacity factor. You know, the capacity factor is the way to measure intermittency. We are talking about the ratio between the actual energy that we produce over 1 year divided by the maximum energy that we can produce during that year if you are at full power. Well, as you can see in the picture, renewables are really with very low capacity factors, something between 20 to maximum perhaps 40% if we are with an offshore wind turbine. And this is, creating many problems, for renewable energy integration. So we really need, to have new renewables that are able to give us a much higher capacity factor for many reasons. The second problem is the low inertia that renewables are introducing in the power grid. And this is a very interesting example. You can see here the evolving the frequency over time of two grids. One is France and the other one is the UK. As you know, France, we have about 70% of the energy produced by nuclear reactors. So in other words, a synchronous machine with very high inertia. However, in the UK, we have today, agreed with that is very close to 50% of renewables, in many cases. So in December last year, it was, an event that was, that we have this Eurotunnel between France and the UK, and we are actually, sending energy, through this Eurotunnel, about 1 gigawatt of power. And suddenly, that was disconnected, as you can see in the slide. In France, almost nothing happened, with frequency because of this very high inertia. In the UK, the frequency, went down dramatically, being very, very close to be a blackout. And that was actually the frequency in London. Something like this, happened in Norway last week. A couple of weeks ago in Portugal. This is something very big that is happening because of the renewable energy penetration. We really need renewables with a much higher renewable penetration. So let me perhaps, be inspired by Steve Jobs. Perhaps we can have a solution for that. You remember probably this historic presentation about the iPhone. That was 2017. I think this presentation changed our lives. And he said, this is a phone. This is also a touch screen. This is also a camera. This is also an iPod. This is also a way to connect, to internet. That was the iPhone moment. And the iPhone hit 1 million sales, in 74 days and changed our lives. And you know what? That was a multifunctional hybrid system. Can we perhaps have the renewables energy moment here with the same concept of a hybrid energy system that we are actually putting together different energy inputs like, wind, solar, wave energy, maybe flywheels, maybe tidal energy, and to different outputs like, providing new capabilities for the power grid, or maybe producing hydrogen, or maybe digital data, or maybe fresh water with very high objectives, maybe capacity factors, damping capabilities, resiliency, and other things. Well, this is the hybrid system concept. And perhaps we can create islands in the, across the country with all these properties like little or big boxes or perhaps islands, having all these capabilities. Now, we have seen, different examples of people coming with, let's say, wind and solar. As you can see there, this is more co-location than co-design. I think that what we should do is more a co-design of the systems. We have other examples, of people just removing, the cables of the floating offshore wind turbine that is very far, and then producing food, or maybe fresh water, or maybe hydrogen, or digital data in the middle of the ocean. So these can be opportunities, but I would like to look quickly at a case study to understand better this concept of synergies. So let's suppose that we have a floating offshore wind turbine, a very good one, with perhaps an LCOE of 10 cents per kilowatt hour. And let's think that we put with this system a wave energy converter, and we co-design these two systems. In other words, the wave energy converter is going to take a lot of the movements of the floating platform, something that we did in the Atlantis program, and we were able, in that program, to reduce the cost of the floating platform a lot. So perhaps this is the physics here, right? That the waves energy converter are taking this and then having a much better LCOE for the floating offshore wind turbine. Let's say that we go from 10 to 9. And let's say also that for the wave energy converter, we already have a floater, so we can go from 25 to 17. Then the question is this a win-win case? Is this synergy or is this function? And for that, I would like to look at a more formal analysis very quickly. In the first case, we have the wind turbine only. So we have some cost, some money in the system, and then some revenue. So we have a profit margin before the hybridization. After that, we have the wind and the wave, and then we have also, money in, let's say that is the same, and then another revenue, so another profit margin. And the idea here is that if the profit margin in the second case is better than in the first case, then we have synergy. And we can put this with some algebraic manipulation in terms of LCOE comparison. So like the LCOE of the aggregated system should be less than the LCOE in the first place. Well, if we apply this to our case, remember 10 to 9, 25 to 17 cents per kilowatt hour, what you can see very quickly is that it can be a synergetic case or a completely a dysfunctional case. And it depends on a parameter that is alpha. And alpha is just the way that we split the money in the hybrid system between the wind energy system and the wave energy converter. So as you can see, this is not intuitive. So if you are coming saying, I have a win-win case because I am improving the LCOE of the wind energy system and the wave energy converter in this hybrid system, well, maybe this is not a good case. Maybe this is a dysfunctional case. So we really need, to think carefully about these synergetic cases. So as a summary, what I am proposing here is maybe the next revolution of renewable energy. Just having all these possibilities of combining energy inputs, having different outputs, maybe electricity with grid ancillary services, maybe it's, the multi-vector thing with freshwater, hydrogen, ammonia, digital data, food, things like that, maybe in islands in the middle of the ocean. And of course, with all these problems that are, ARPA-E hard, this co-design, this co-location, this control of these systems. So this can be, perhaps a new program at ARPA-E. We already had, a couple of days ago here, a workshop about these concepts. So this could be maybe like the iPhone, the iPhone moment, maybe this is the renewables energy moment. So please send me your ideas. You have my email there. I really would like, to have your opinion about that, to really put together here a very strong and big program around energies, to fix many of the problems that we have today with this next revolution of renewables. Thank you.
Right, thanks everybody. I think I'm pumped. What about you guys? We pumped? Yeah. All right, yeah. So this is the future, man. This is the future of electricity transfer. So we got a bunch of questions already, so thanks for submitting those. So I'm gonna try to sort of coordinate this a little bit. But with Jack. Jack was first, and there were quite a few questions, Jack, on what about nuclear, and what about refueling some of the existing generation side? Do you want to say a little bit about that?
So I think my main point is we all understand the role electricity can play in the future, but the electric grid delivers about 15% of our energy. And if we want to make a transition to a green future, I submit to you, we cannot afford to replace everything that's associated with fossil fuel, whether it's the grids or the end-use devices. So think about the role electricity can play in terms of making molecules that can reuse these assets. Because it's cheaper to move the molecules than to move the electrons. We all recognize that, but it's also going to be faster to keep using the hardware we have. I submit to you, it will not be fast or green to replace 250 million vehicles and rewire 80 million homes. So our goal is to go fast, cheap, and green. Let's continue to do all the things we're planning to do with the electric grid, but figure out what's the role of molecular fuels and ideally drop-in fuels so we can use what we've already got.
Right. Thanks, Jack. Yeah, I mean, that is a key area. What can we sort of repurpose in a way? So I got a few questions also for Peter. Peter, they're talking about, moving the, you talk about moving the electrons around physically with energy storage devices. And the question was, how do you get it inside the cities? How do you anticipate, moving these trains inside the cities where the energy is needed, right? The energy is needed at the load centers.
Yeah,
and
sure.
how do you move that amount of energy into the centers and get it connected?
So one of the nice things about this vision is if you look at a solar farm, they produce somewhere around 1,000-volt DC, right? So in our current traditional mechanisms, we take that 1,000-volt DC and use transformers and all kinds of DC to AC conversion systems. And I do like the super HVDC superhighway, but that's a lot of equipment to get it to that last state. When we get our arrival point, we want to take it into new applications. Data centers will run well off DC. If you have a system that can provide in your energy storage system and transfer it at that 1,000-volt DC all the way, you don't need any of that conversion. You can hook that up either at the substation. All you need is a substation or significant electrical infrastructure near rail, road, or waterway, which is quite a lot. Or you can even put it behind the meter, which completely resolves any potential right-of-way or other issues. If you're a small business and I can say, would you like to run your power off an energy container? I can drop in your parking lot and run that for about 2 years of Iowa wind power at 5 cents. I think that could be appealing if you live in California. But you can also do it at the substation at the regional level. I think the vision is greater than just the containers. It's really about how do we start moving electrons in the future? And my vision is that it will be more than just through wires.
Right. Right. I mean, that's, thank you. And maybe a question about, what about safety? Do you think there is safety concerns putting all the storage batteries and so
Sure.
on?
I mentioned the number one requirement is safety. The second one is the energy density, because that's the economics. What happens when there is something that wants to discharge? It wants to find its way to ground. If I'm on a railroad track, that's not too far away from me. But there are mechanisms you have to really explore that it has thermal runaway shouldn't occur. We already have that requirement in our Propel 1K vision, and we need to just expand that further into systems like this. And I really like that second part where we're exploring modalities where something can be an active state of charge-discharge, right, and then can turn into a sleep mode. So I'm not necessarily saying batteries only, but energy systems in general, if they only operate to charge or discharge at a certain temperature or pressure, that means when they're not at those temperatures or pressure, they can be in a passive mode, and that would be ideal. So I want people to explore what kind of mechanisms could do that, and think very broadly, how can we move energy in enormous ways around the country using the infrastructures that we have.
Right, thanks Peter. There was a question which actually sort of addressed both to Olga and myself about data centers. So data centers is mentioned as being big future consumer of electricity. Why don't we build the data centers closer to the generation? So that's a good question. Maybe Olga, you can start. I will chip in.
I think that when the Microsofts and Googles of the world are courting small modular reactors, things like that, that's an attempt to do that. That's an attempt to bring generation to the data center without having to worry about utilities running that connection. So they're trying to do that. There's another aspect. Data centers also want to be where the data is, where the data interconnects are, and so sometimes that's there already. Northern Virginia, which is why all the data centers want to be there because of the latency. In some applications that's critical, others maybe not so much. So I think that's a viable strategy. It's just that you need to be able to bring generation and whatever interconnect that entails to your data center, or just minimize the need for the interconnect.
Right, yeah, and maybe my suggestion to that as well, we have to do both. I mean, wherever we can interconnect, you know, Synergy's point to Mario's point, wherever we can build something together with generation without using transmission, absolutely, absolutely, that synergy should be there. But it's not always possible, right? So as Olga mentioned, it has to be close to where the data is. There is a follow-up question, Olga, for you about the electrical interconnects are a lot smaller physically than optically. How can you solve this size, size issue with your optical computer solutions? How can you use optical computer solutions to solve it, I guess, the real question. Yeah.
So certainly traces on the chip are smaller than a fiber, but the silicon photonics allow you to do optical circuits on the chip that start being sort of in that right, micron-ish size, size range. And furthermore, you get a lot more data through same physical channel optically, so they may be bigger, but they're bigger pipes for data, right? So maybe the traces are smaller, but you need more of them, and you kind of have to consider the specific scenario, and that's what I mean about that crossover. You can run lots and lots of parallel traces, and a lot of the 3D interconnects kind of play that electrical game, but I think as your efficiency of conversion improves and you consider the fact that you can get a lot more data in the same physical space, then you start really playing, you have to consider it very carefully because you might be entering a place where it makes more sense to do it optically than electrically.
Right, thanks. Mario, there are a few questions coming in for you as well. So the first one is, given the ease of moving electrons from one point to the other, why do you want to co-locate electrical generating plants, of different types, wind and wave and so on, if you can move it with electrical grids?
Yeah, well, the answer is clear that it depends on the distance. So if let's say that we are in a floating offshore wind turbine very, very far from shore, then the electrical connection is really very expensive. The floating substation as well. So perhaps, a good solution for that is really to do other things over there. Perhaps is this data center, that is in the middle of the ocean, that is also was in the previous question, so, or is, for other things, maybe we can be producing hydrogen and we have vessels, just moving this hydrogen to different places in the world, and then we have a different business model here. So I think that this concept of synergies is opening, the door to many different approaches and new business models as well, so, but in terms of the interconnection, it depends very much on the distance.
Right. Mario, there's a follow-up question. It's about distributed energy generation, right? So at the point of demand, rather building, distributed energy there, is that part of your vision? If you think about a residential application, putting solar batteries, is that part of your vision to really co-locate distributed generation as well?
Well, I think that the key part here, just to summarize that, is the co-design of the systems. So my vision is not just having systems that are working in parallel and then you connect to the grid eventually, is to have a different animal, to a new system that we take advantage of the physics in order to end up with a different system, a different renewable energy system, perhaps for different outputs also, and that can be part of the design, but essentially for critical objectives. So it's not for the sake of combining things, it's for opening the door to really achieve objectives that we are not able, things that we are not able to do today. So this is I think the vision for this.
Right, right. So I guess our time is up, but there's a bunch of questions which we couldn't answer, guys. So don't hesitate to send this to to us individually or as a group. I know there was questions about the sun is shining all over the world. Why don't we build a massive, HVDC grid? I like that. Whoever said that, that's great. And is it more cost effective to do that than storage? There's also a question about energy efficiency. What's the energy efficiency of all these different aspects, including Peter's effort of doing this via trains. But our time is up for today. I do thank you all for engaging with us, and continue to engage with us. We will have coffee with ARPA-E tomorrow again, so come back with your solutions and discussion. We're looking forward to that. Thank you very much.